Okay, so in this lecture I'm going to discuss about linear operator, eigenvalue and eigenfunction. First I'm going to solve this eigenvalue problem or differential equation. Maybe we can just denote the or identify the operator. So if I write a is d square, dx square is a linear operator. So then I can say a phi plus lambda phi is 0. To solve this equation, we can look at the characteristic equation first. So it is a second order differential equation. That's its characteristics equation, which means m is plus or minus square root of lambda times I. Lambda is positive, so when you take it to the right hand side, it becomes an imaginary number, and the solution will be sines and cosines. Plus b sine square root of lambda x. Okay, and using boundary condition, so you set phi 0, which is 0, set x equals 0, cos 0 is 1, plus sine 0 is 0. This gives you first coefficient a is 0, so phi is just sine. Okay, so now you use the second condition. Okay, so b sine square root of lambda L, and this equals 0. This can only be 0 if it is sine n pi. N is any number, and we're going to take a positive number from 1 to infinity. Okay, so that means you can just b cancels out originally because right hand side is 0, is n pi, which gives you lambda is n square pi square by L square, n goes from 1 to 3 and so on. And obviously you see that if n increases, lambda increases. The lowest value of lambda is 1. Lambda is for n equal to 1. So lambda 1 is lowest eigenvalue. Okay, and all other eigenvalues are greater than this value, and eigenvalues are positive. Eigenvalues are positive in this case. And eigenfunctions are, let's say, nth eigenfunction without using the coefficient p will be sine n pi divided by L times x. So that's the eigenfunction. And you can see that sines are orthogonal, so eigenfunctions are orthogonal. So that's pretty good, and this is very interesting result and very useful and very easy to understand. You have a second order linear differential equation. You just get the characteristic equation, and based on the characteristic equation you find the solution, apply the boundary condition, and you can find the eigenfunctions and eigenvalues. Very standard, very easy. Now I want to look at this equation, and I want to show that eigenvalues are positive without solving or without determining the eigenvalues. So let's think about how we can do that. And maybe if we know how to do that, then we can apply this technique for other equations, maybe a few other equations. It may not be for every equation the same trick works, but it will work for some more equations. Okay, so multiply this equation. That's the trick we'll be doing here. Multiply by 5. So after multiplying, we want to integrate it, but then before integrating, we manipulate the first term. So maybe we can think of d dx phi d phi dx, but this is not exactly equal to phi d square phi dx square. So this term is not equal to this term, so that is an additional. So if you do the product rule, phi, and you differentiate that, you get phi d square phi dx square, but then you get plus d phi dx times d phi dx. So how about we subtract that additional term, d phi dx d phi dx, okay, plus lambda phi square is 0. So what we see here is that we can now integrate it, and if we integrate, the first term is an exact differential, so that will be just the boundary value. So you evaluate that integrand on the boundaries. Second term, let's write it down, d phi dx dx plus okay. So by using the boundary condition, because we know the boundary conditions are phi equals 0, which is 0, so this term will be 0, phi equals L, phi at L is 0. So the boundary condition implies that the first term is 0. From the last two term, you can see that lambda is constant in the last integral. That can be taken out, and you can write and definitely it cannot be 0, it cannot be negative, because you are is a definite integral, and also you are integrating positive quantities, you are integrating a square term in the numerator in the denominator, so that's obviously is greater than 0. Of course this could be 0 if phi is a constant, but anyway, so that is how I have proved that by multiplying the equation with an eigenfunction, and then I integrate it. It is just I tried to manipulate the product rule. In several cases we can utilize this technique. Next point, I want to show that the eigenfunctions are orthogonal. So I have eigenfunctions phi 1, phi 2, and so on, 1 to infinity. I have an infinite number of eigenvalue. For each eigenvalue, I have an eigenfunction. Okay, so the eigenfunctions are orthogonal, meaning that you take an eigenfunction phi n, take another eigenfunction phi m, integrate it from 0 to L, which is the corresponding interval, and then you get 0, if phi n is not equal to phi m, which also means that you can say lambda n is not equal to lambda m, because each eigenvalue corresponds to an eigenfunction. So eigenfunctions are different, meaning eigenvalues are different. So if you take two different eigenfunctions, is equivalent to taking two different eigenvalues. Okay. So how do I work it out? So remember we discussed earlier one property of linear operator is some linear operator can be self-adjoint. The adjoint operator could be just itself. So it's like self-adjoint. And this given eigenvalue problem is self-adjoint. That is what we have learned already, because it is a very simplified Sturm-Liouville problem is self-adjoint, meaning that if you integrate from 0 to L, the operator we use just uppercase A for the operator. So you calculate this quantity, operate by A onto a function V, and multiply the result by another function U. And now you switch the order. Okay. And both results will be equal if L is self-adjoint. Let's try it for the eigenfunctions. See what happens. Okay, since the operator is self-adjoint, then it satisfies this property for its eigenfunction. So you take any eigenfunction phi n, phi 1, phi 2, phi 3, whatever it is, take another eigenfunction phi m, phi 2, phi 3, whatever it is, and then construct this equation. Now, because this is an eigenvalue problem, we can say A times phi n, or A operates on phi n, is minus lambda phi m from equation, right? And phi m, this will be minus lambda n, this is minus lambda m, minus lambda n phi n dx. So it is because let me just write it down here. So this is the equation, and in terms of the operator A, lambda phi is 0. Okay. So we can take lambda out. So on the left hand side will be negative lambda m out, phi n phi m dx. On the right hand side, negative lambda n taken out. Inside will be phi m times phi n dx. Okay. You can take both right side to the left hand side, and then you can take lambdas out. Okay, so then you can write this equals 0. And definitely you can say if lambda n is not equal to lambda m, this integral phi n phi m dx is 0. This integral is 0 if lambda n is not equal to lambda m, which implies if phi n is not equal to phi m, or the eigenfunctions are not equal, eigenvalues are not equal, is equivalent to saying eigenfunctions are not equal, and when they are not equal, if you integrate, you get 0. You say this is orthogonal. Obviously, if they are equal, then they become square, and if you integrate a square, you will not get 0 unless it is 0. So eigenfunctions are not 0, which is a trivial eigenfunction or trivial solution that we don't consider that as eigenfunction. Okay. So in the second part of this exercise, you have seen that if I have a linear differential equation which is self-adjoint, Sturm-Liouville problem, then I can show that the lambdas are positive or eigenvalues are positive without solving the problem. And I can also show that, prove that mathematically, because the operator is self-adjoint. So without solving the problem or without proving the integral of the eigenfunctions multiplied, two eigenfunctions multiplied, the integral vanishes or do not vanishes, without do the calculation, I can mathematically prove. And then the trick I have used is by considering self-adjoint property of the operator. If you have any question, or if you do not understand any part of the exercise, please let me know. Thank you.